Okay, yeah, in the residential class, I forgot to record, so I'm gonna just kind of, go over notes and then just kind of making a voiceover, okay? So, so far we have discussed mainly on time-dependent solution, okay? So in this case, like consider just infinite potential well, okay? So put infinite potential well is essentially described as this one, right, so far. When at x equals 0, infinite potential well is located, and at x equals d, infinite potential well is located, okay? And for this case, the wave function or solution for Schrödinger equation is given as that, right? And then when we consider time-dependent term, now we have to, couple with the time-dependent term that is given as this one, right? Psi n over x and then phi of t. This one is the solution by solving time-independent Schrödinger equation, right? This one is only space-dependent, and then this is a time-dependent term. Yeah, do you guys recall like how we got this expression? Like a full Schrödinger equation. It's a partial differential equation, that is dependent on time and space, and then, to solve that, we use the separation of variable, right? We basically kind of, describe as space-dependent term and time-dependent term, right? And then that is how we were able to get time-independent Schrödinger equation. So with that, we have time-dependent term here, and then the solution, we already obtained it. So in the sense, time-independent solution written here first, and then multiply by time-dependent term here. And then for the infinite potential well, we already know allowed energy levels, which is given as that, right? And then so far, we were looking at, specific n values, okay? So in that sense, this is really kind of each mode, okay? But in reality, many modes or different n can be excited simultaneously, okay? So, like the condition for that is, like as long as the wave function satisfies boundary conditions, these many modes can be excited, okay? So for any function, in this case, let me just kind of start with the stationary part. Okay, for the stationary, and then also for the case of infinite potential well, this any function can be described as linear combinations of all wave functions. Okay, so wave function is written here, and then we can sum up any wave functions with some appropriate constant values. Okay, so in the sense, psi n for infinite potential well, we already know that is square root 2 over d sine n pi over dx. Okay, but here we have to know appropriate values of Cn, and how are we going to find that? That is essentially, the approach we are taking here, to find the Cn, the Cn can be obtained, but here is essentially kind of a short proof. Let us now just consider integration from negative infinity to infinity, and then we multiply by this psi m star. Okay, this is the complex conjugate of wave function, and this fx is just any arbitrary function satisfying boundary conditions. Okay, so with that, we basically plugging in this f of x into here, then we can simply describe as in the summation n equals 1 to infinity Cn and integral negative infinity to infinity psi m star and psi n dx. And then this one is essentially Kronecker delta, and then this one can be proven, and this is actually one of the homework problems that will be given to you, and it turns out this equation is simply Kronecker delta. Okay, if you're not familiar with this Kronecker delta, this is just nothing but the value. Okay, the condition is if these two values are the same, it spits out 1. If these two values are different, it gives you 0. Okay, so then if you just take it for granted here, this can be written as summation n equals 1 to infinity Cn delta mn, right? And then this one is essentially, can be expressed as C1 delta M1 plus C2 delta M2 and so on. And this one will be eventually just a Cm. Why is that? Like suppose this M is 2, okay? So what that means is that when M is 2 here, 2, 1, right? In this case, m and n values are different, is 0. But in this case, if m is 2, when we plug it in, delta 2, 2. So these two values are same, so this one term survives, right? And then, but for all other terms, it will be 0, right? Because the m and n values are different, okay? So what that means is that only when n is m values, it survives. For all other values, it's 0. Okay, so in this case, this Cn is simply, look at this one, this Cm, and then this one, and m is anyways just kind of a variable. We can just simply replace this m with n value. So Cn is simply integration negative infinity to infinity and psi n star f of x dx. Okay, so this is how you can find out what the constants should be. Okay, so then now if we consider time-dependent term, and then also for infinite potential well, psi x comma t is, like we put down this term here, like linear combinations of wave functions multiplied by time-dependent term. And then we consider the initial condition first, okay, being like t equals 0. So then, this term is 1, and then we have n equals 1 to infinity, Cn psi n of x. And then from here, you can find the Cn value. Okay, Cn is again infinity, negative to infinity, psi n star, complex conjugate, and then psi x comma 0. Because this is essentially, like any arbitrary function, right? So that is essentially f of x. So, regarding this problem, you will be able to solve the homework problem. Okay, this is a homework problem. The arbitrary function is given as a parabola here for the infinite potential well. And then if you actually draw this plot, x equals 0, then basically that is a 0, x equals a, 0, and then it's a kind of inverse parabola, right? And then you will be asked to find a. Okay, you can find this a using normalization, and then you'll be asked to find this psi x comma t, okay, time-dependent term in terms of wave functions. Okay, so for that one, obviously you need to find the wave function itself, but we already know what it is for infinite potential well. And after that, you have to find this constants for linear combinations. And once you find that, you can kind of couple with time-dependent term, and that is how you can write. Okay, this is a kind of the simple way to kind of solve the equation or solve the problem. And I have actually the simulation that I want to show, but for this one, yeah, we can work on that next week. Okay, so that's it for today.